Hey everyone, I hope your week has been going well and that you're making some progress with the R computer program and with the material in the textbook. This week we jump into simple regression. We are going to be learning the most basic form of regression, which is fitting a straight line through a set of data. So we're going to learn that in two steps. This first lecture will be on the basic technique of regression, which is finding the line of best fit through a data set. And then the second part is going to be on some principles in hypothesis testing. So get your pens ready and we will get started.
We're going to begin by looking at figure 2.1 in the textbook. Now, this is a graph that shows data from 123 utilities in the United States. On the horizontal axis, we have the output in millions of kilowatt hours, and on the vertical axis, we have the operating costs in millions of dollars. So these are electrical utilities, and the more output they create, not surprisingly, the higher the cost goes. You can see there's an upward sloping scatter plot between the two of them. So let's talk about the process of building a model to represent that relationship statistically. So we have output X and we have costs Y, and so the simplest possible model would be we want to explain costs. So that's our dependent variable here. We want to explain the costs. So the simplest possible model would be that the costs of any particular utility, so I equals 1 to, in this case, 123, that's in our sample, the cost just equals the average, plus an error term. Okay, so Y bar, that's mean costs, and E with a subscript I, this is the unexplained random term. Okay, now this isn't a very good model. Because we obviously saw that there's an upward sloping relationship between the output level and the costs. So we can really do better than just say our model is going to be that the cost is the average plus some random error term. But I write this down just because it's good to have in mind that that's the reference point for the worst possible model. Okay, so this is the worst model. And it assumes we can't explain anything other than the mean. And if we go back to the figure, so the idea here would be if you had this data and somebody said, okay, well, we've got a utility, we've got this utility here represented by that dot, that observation, and that utility, their operating costs are about 50 million a year. And then we've got the utility represented by that dot, and their operating costs were 250 million a year. So why are they different? Now, it would not be a very good answer to say, I don't know, it's just a random difference. Everybody has an average of about 120 million, and some are below it and some are above it, and it's just random. Well, that's not a very good answer, because obviously the real explanation is, well, this utility only produced about 12 million kilowatt hours, whereas this utility produced about 55 million kilowatt hours. So that's why this guy has much higher costs than this guy, because our output was different. Okay, so let's make a model that takes into account the ability of output to explain some of this difference. So the model could be a simple linear equation. So we'll say a better model. We'll say yi equals alpha plus beta xi. Okay, now what's making this a better model is uses the information in X to explain Y. Now, this is a model, and what that means is we're just assuming that they follow a linear relationship. We don't know for sure what the function is that connects operating output to costs. It may be a more complicated function than this, but we're going to assume it's a linear function. And so, given this function, then we would need to use the data to pick the values of alpha and beta that make the most sense. And we can be more precise than that. We can say, let's pick the values of alpha and beta that will minimize the sum of the squared errors that we make. All right, so keep that in mind. Let's say we've gone through some kind of estimating process, and we get alpha equals 2 and beta equals 5. Just made those up. Those won't likely be the right answer. But that means that our model now is y equals 2 plus 5x. I'm going to put a subscript on there. So that means if x equals 1, yi equals 7. Okay, so now we have a model. So we have a model that says if you give me the value of x, I will predict the value of y. However, it's never the case that a model gives you perfect predictions every time. There's always going to be these little discrepancies. So when we construct the model, we need to add in the error terms. And I'll use the little epsilon, so that's a Greek E. And we're going to call that the error term. Okay, so now we have a complete model. We have the variable we want to predict. We've got the explanatory variable and the function that we're going to use, in this case a straight line, linear function, and we have the error term. And the error term is just going to absorb all the stuff that we didn't explain. So if I switch this over to a new page, the model is y equals alpha plus beta x plus epsilon, and this is called a regression model. Now, why regression? Why do we use that term? Well, it comes from a long time ago. Somebody did a study trying to explain the height of men. I think it was in England. So the height of men, and so the height of a man in the sample, and he compared that to the height of the father. So he took a man's height, and then he found out the height of the man's father. Now, if every man was exactly as tall as his father, then all the data would lie on this 45-degree line. So then that would mean if he told me that a man's father is 5 feet 10 inches, then that would mean his son will be 5 feet 10 inches. But it's not the case that every man is exactly the same height as his father, but they're correlated. So tall men tend to have tall sons and vice versa. And so the data kind of spread around this 45-degree line. And the author of this study said it's like the numbers are being pulled onto this 45-degree line. There's a tendency for them to regress to the mean. And so this term regression comes from the idea of the data regresses towards a straight line that passes through the data. Regression to the mean. So that's where the term regression comes from. So let's fill out the terminology a little bit for our model here. Let me just rewrite it so I have a bit more room. We have, in our terminology, we have alpha plus beta x plus epsilon. The variable on the left-hand side, the one that we're trying to explain, we're going to call that the dependent variable. Its value depends on the values on the right-hand side. We have these coefficients here, which we will call coefficients. They're also sometimes called parameters. We have, so that's the dependent variable. X here is the independent variable. So it's an independent variable, but we will also call it the explanatory variable. Okay. It's independent in the sense that it came from outside the model. We got data on the output of the utilities. The cost depends on the output. And so the independent variable helps explain the dependent variable. So we'll use these terms interchangeably. Explanatory variable meaning we're going to use X to explain the changes in Y. And then we have the error term. Now, we're also going to encounter the term residual, but the error term and the residual are not going to end up being the same thing. When we fit a regression model, pointing up here, we will have residuals in the regression, and the residuals will be estimates of the error terms. But right now I'm writing down the model, so I'm going to refer to that as the error term. And so the error term then is just everything that can explain changes in the dependent variable other than the independent variable and the coefficients. One final point is the idea of causation. Does X cause Y? It may be, but the regression model doesn't establish that. So when we fit a regression model, you may get plausible looking values for alpha and beta, and then that may mean, okay, this is a good model, we're going to use that to allow us to predict Y given the value of X. But that doesn't mean we've proven that X causes Y. Causation has to be established with a different type of argument that really comes from outside the model. So there needs to be some kind of theory that explains or that says X causes Y. Otherwise, what we're really doing is looking for correlational evidence. Now, it's safe to say that if there's absolutely no correlation between X and Y, then X does not have a causal effect on Y. But if we do find a correlation, that on its own doesn't prove that X explains Y. We have to have other theoretical reasons for that. So, this is our basic structure of a linear regression model, and next we're going to talk about how we estimate these coefficients alpha and beta. So, what we are looking at now is the question of estimating a regression model. Sometimes we'll refer to it as fitting a regression model, and in particular, so we go back to our regression equation. What we want to do is estimate alpha and beta. And when we've done that, the results are called alpha hat and beta hat. The hat is the indicator that we're looking at the output of a regression estimation. Okay, we've picked the values of alpha and beta that we want. And what do we want? Well, we want values that fit best. All right, so we have our model. Okay, so that's the basic model. Now, when we've picked them, what we will have is alpha hat plus beta hat x. And because not every observation of y is going to fit exactly on the regression line, then we will have these residuals. Okay, so I mentioned the residuals are the estimates of those error terms. So this refers to the true values, and this refers to the estimates. And so far we have not talked about how you actually choose the values of alpha hat and beta hat. We will get to that. Now what if we just take the output of the model and we don't include the residuals? Well, we'll put a hat on y then in that case. So this would be the fitted values. So let me just draw a little picture here. So we have x down here, we have y up here, and we have a few data points. Okay, and you can imagine we're going to put a line through the data points. So that line is alpha hat plus beta hat times x. So it's a linear function. So the fitted values are the values of y that lie right on the regression line. And then a point like this will be yi equals alpha hat plus beta hat xi plus, I wrote e rather than epsilon, but it doesn't matter, plus this residual term. And the residual term is this distance. Okay, so we're taking our original data and we're relating it all to that straight line to that regression model. So let's look at these residuals a little more closely. We have the residual is yi minus alpha hat minus beta hat xi. All right, and, so I got that just by moving these two terms over to the left-hand side of the equal sign. So those are the residuals. Well, suppose I take the sum of the squared residuals. Why would I do that? Well, remember when I talked in the beginning lecture about choosing the best value of the mean, and we defined the best as the one that had the smallest sum of squared residuals between the mean and the observations. So we're going to do exactly the same thing here. So we'll take the sum across the whole data set of the squared residuals. Okay, so that is the sum from I equals 1 to n of y minus alpha hat minus beta hat x squared. We could, if we wanted, write this as yi minus yi hat squared. So this is the sum of the squared residuals. It's the sum of all these vertical distances squared. And what we want to do is pick the values of alpha and beta that gives us the smallest sum of these squared vertical distances. And that's a calculus problem. We want to pick alpha hat and beta hat to minimize the sum of the squared residuals. Now, we won't go through it. All we'd have to do if we were going to do the calculus problem is take the derivative of this expression with respect to alpha hat and with respect to beta hat. That gives us two first order conditions. We set them equal to 0, and that will give us a formula. So it would allow us to take the data on x and y and spit out values for alpha and beta. So we're not going to actually solve that problem, but you will see the formula. I will show you what the formula looks like. If we did, it yields yi hat equals 2.19 plus 4.79 xi. So that figure you saw in the textbook, if you fit a straight line through the data and you use an intercept of 2.19 and a slope of 4.79, that straight line will fit the data best in the sense of minimizing the sum of the squared residuals. Now, when we've done that, when we've fitted a model and we've got our coefficient values, then there's things that we can do to interpret the results. So the intercept, in this case, is 2.19. What that means is, in this sample, if you had a utility that didn't generate any output over a year for some reason, it would still have costs of 2.19 million, or at least that's what you would predict. So it's got certain fixed costs, in this case 2.19 million. So these are the costs if x equals 0. But you have to be careful with that. You have to be careful when you interpret an intercept, because oftentimes the intercept is way outside of the sample and it may not actually be a very meaningful number. So in this case though, the sample does actually go pretty close to the intercept, so it's not a bad estimate. However, we're mainly interested, usually, sorry, that's kind of messy, mainly interested in the slope parameters. And the reason is that beta hat equals the change in y, or in this case the change in yi hat, for a given change in x. And that means it is the marginal effect on y from a change in x. So what that tells us is, for these utilities, if output goes up by 1 million kilowatt hours, then the costs will rise by about $4.79 million. So it would then put us in a position where we could say something to the operators of the utilities if they're asking what's the impact on our costs by our output going up and down. And you can say, right now, given the behavior of these utilities, if the output goes up by 1 million kilowatt hours, on average we expect the cost to go up by $4.79 million. Okay, so just to recap what we've done so far, and most of this is terminology. Okay, linear functions are very simple, but the terminology is going to be with us all the way through. So let's make sure that we have the terminology clear. So we have data points on y and x, and we think that they're related, and we're going to propose a linear model to relate them. So the linear model has an intercept and a slope, and these are the coefficients, and it has error terms, because the linear model doesn't explain everything. There's other stuff going on, including just randomness, and so we have an error term to account for the distance between our model and the observation. Then we get estimates, and the estimates use alpha hat and beta hat, and we will look at the formulas later for how to estimate those using the data. And then there will be a distance between the regression line and the observation, and that is the residuals. And then we have fitted values, which is the points right on the regression line itself. And the rule that we use to choose alpha and beta is to minimize the sum of the squared residuals. And that's a calculus problem, so we are choosing alpha and beta, alpha hat and beta hat, to minimize the sum of the squared residuals. So that is the basic outline of simple regression. So let's talk now about measuring the fit. Okay, what do I mean by that? Asking how good a model is this? How well have we done? Do we have a regression line that explains a lot of the data, or is it not a very good model? So let's go back, recall the simplest model or the worst model. And that was y just equals the mean plus errors. Okay, so that would be the case where if someone says, can you explain the different costs of different utilities, and we say, I don't know, it's just everybody has sort of the average, plus or minus some unexplained error term. The sum of the squared residuals in this case, we'll call that SSR is 0, I'm going to put a 0 subscript there, would be the sum of the squared residuals, and that is the sum of yi minus y bar squared. Okay, so the basic sum of the squared residuals. Okay, now use the linear regression. So here the model is alpha hat plus beta hat xi plus our regression residuals. Okay, and now the sum of the squared residuals, I'll put a 1 there, subscript 1. Sum of the squared residuals is the sum of epsilon hat squared, so that is the sum of y minus alpha hat minus beta hat xi squared. Okay, so if this is a better model than just the simplest one, then this term should be a lot smaller than this term. Okay, so if the regression model has explanatory power, SSR1 should be less than SSR0. If it isn't, if the two of them are about the same, then that tells us our linear regression didn't really teach us anything. It didn't really explain anything. So in order to make use of this concept, I'm going to relabel this one here the total sum of squares. Total in the sense of this is everything that we are trying to explain. So in this model, we haven't really explained anything. We've just said, we don't know. The costs vary strictly by random. You can always estimate a mean, but other than that, we don't know. So this is the total sum of squares. And now we've got the sum of the squared residuals, which is the part that wasn't explained by the regression model. So if we take the total sum of the squares, minus the sum of the squared residuals. Okay, so that is the sum of squared residuals from the model. So this is everything that we need to, this measures everything we need to explain, and this measures everything that we didn't explain. So what's left over is what we did explain. So we're going to call that RSS, which is the regression sum of squares. Let me jump to a new piece here. I'll just rewrite all those. So we have the total sum of squares. That's the sum of yi minus y bar squared. And we have the sum of the squared residuals. So that is the the sum of yi minus yi hat squared. And then we have the regression sum of squares. Well, it turns out that is yi hat minus y bar squared. Okay, so total sum of squares, sum of squared residuals, regression sum of squares. And they are related. RSS plus SSR equals TSS. So the regression sum of squares and sum of squares residuals equals the total sum of squares. So what we're often interested in is how big is the regression sum of squares compared to the total sum of squares. So an easy way of measuring that is to take the ratio of the two, RSS over TSS. And we're going to call this R squared. So R squared is the fraction of the variance in Y explained by the model using X. And you could also write it, R squared equals 1 minus the sum of the squared residuals over the total sum of squares. These two are the same because total sum of squares equals those added together. So R squared falls between 0 and 1. So why is that? Well, suppose that we have a really amazing model. Suppose we have a regression model that explains everything, which means all the observations lie exactly on the regression line. Well, if that's the case, if we have a perfect model, then the sum of the squared residuals equals 0. So then plug 0 in here and you get R squared equals 1. And if we have, let's say, a useless model, well, that would mean that the sum of the squared residuals is the same size as the total sum of squares. So then this ratio would be 1, so then we'd have 1 minus 1. So then we would have R squared equals 0. So if the sum of squared residuals equals 0, then R squared equals 1. If the sum of squared residuals equals the total sum of squares, then R squared equals 0. So, regression model, linear regression, estimates, and now we have R squared. And R squared is a summary statistic that tells us the fraction of the variance in Y explained by the model using X. Okay, so we now have a regression model, alpha plus beta X plus our residuals. We've estimated alpha hat and beta hat, and now we want to ask how accurate are they? Okay, so you'll remember that with the utility model, we said beta hat equals 4.79. Well, is it exactly 4.79? Maybe it's 4.80, or maybe 4.90, or maybe it's 5.01. Or we could go the other way, maybe it's 3.79, or 2.79, or maybe it's 0. So these are just estimates. The regression method gives us point estimates, but chances are it's not exactly 4.79. So what we need to do is be able to ask, okay, how accurate is this and how confident are we, first of all, that it's not zero, that we aren't just deceiving ourselves and finding a pattern here where none exists. And if it is not zero, how big an uncertainty band should we put around here? Could we say, well, it might be 4.9, but we can certainly rule out 2.79. Okay, so that is the issue of estimating the confidence interval around our beta hat estimate, and that is what we're going to take up in the next lecture.